All right. That's enough. This is my time to shine. So we had a test last time, and I owe you a lab exam and thank you. A lab exam and a regular exam. I think hopefully I'll have them both back on Monday, but I don't have either of them done yet. I'm about halfway through the lab test. So who remembers what we were doing before the test, getting ready for the test? That's not remembering if you look. Newton's laws and Newton's third law. And then the last thing that we did on the last class was talk about the incline thing. So if you have rolling or sliding along an incline, make the y-axis, the positive y-axis, out of the incline, the surface. And the x-axis parallel to the surface. I can't wait for that Zamboni to come down that hallway. And the benefits are that you have the normal force is just 0n, and that's always what it is. The acceleration, we're always just going to write that as a0. And the one downside is that the weight requires cosine and sine now. Okay, so let's go through. Were we in the middle of an example, or had I done an example? I finished it. Okay.
You did the 50 kilograms and going up 100
meters. Okay, I did that one. So let me do one more. So let's say that there's an object, 10 kilograms, being pushed against the wall, and let's change that to having wheels. And let's say there's a force going this way of 20 newtons and a force going this way of 50 newtons. And we want to know what are the acceleration as a vector. And second, what's the force vector applied to the cart by the wall? Well, even though this isn't rotated, this is rotated at 90 degrees, I'm still going to make the positive y-axis go out of the surface. So that's the y-axis. And in order for this coordinate system to follow the rules, that means that the x-axis has to be up. Any questions about that choice of coordinate system? Okay, so now the free body diagram. There's a weight force that acts straight down, and it has a mass. It's a total force of 98.1 newtons. Then there's the upward force of 50. The force to the right of 20. And then there's a pushing contact from the ground. This is the normal force. I'll call it N. And if you go around the boundary, there's nowhere else that the outside is in contact with this, so that's done. And now we'll go to Newton's second law. Okay, so now all of these we have to think in terms of like those vector problems. We have this funny orientation of the coordinate system, and we're representing these vectors in that coordinate system we're not so used to. Okay, so that 20 Newton force, that 20 Newton force is in the negative y direction. Do you see that? And so that force we're going to write as 0, negative 20. The 50 Newton force is in the positive x direction. So that's 50, 0. The normal force is in the positive y direction, but based on what I said about the benefits, we already knew that that had to be in the positive y direction. That just always is how it works out. So that's 0n, like it always is. And the last thing we have to do is the weight. The weight in this case is in the negative x direction. Do you see that? Someone who's not nodding their head, tell me how you feel about the weight being in the negative x direction. I think it's sort of funny. Tell me what your feelings are. You think it's a little funny? It is a little funny. It's still down, right? So choosing, when we choose our coordinate system, it doesn't have any effect on what gravity does. It just changes what the components of it are, that we sort of a naming for it. If you don't see what I'm saying about it being in the negative x direction, you can think of it as just like all those vector problems that you did. We have a force going this way of 98.1. And we have a coordinate system like this with x this way, y this way. And so what's the angle to get from the positive x-axis to the vector? 180. And so it would be 98.1 times cosine and sine of 180, which would give you negative 98.1 x, 0 y. that's all the forces, and then that's equal to the mass, 10, times the acceleration, which is always going to show up as A0, because all the motion has to be just along the surface, which is aligned with the x-axis. And so we get two equations. The x equation says 50 minus 98.1 is equal to 10a. And so negative 48.1 is equal to 10a. And so a is equal to negative 4.81 meters per second squared. And then if we want that as a vector, we know that this is the acceleration vector. And so we can just plug that variable in. And we get an acceleration vector of negative 4.810 meters per second squared. Any questions about calculating the acceleration vector?
Why didn't you use the mg cosine 90? That's technically not horizontal.
Well, if you think back to the vector problems, what really matters in calculating those components is the counterclockwise angle from whatever x-axis we're using to the vector. So that vector is down, and in this case our x-axis is up. We're not used to that, but now the x-axis is up. So the angle to get from the positive x-axis to the vector is 180 degrees. And so if you take 98.1 times cosine and sine of 180, you get this, negative 98.10. So if that stuff is confusing, you know, glance back at the vector practice problems and just, you know, remind yourself that what we're doing here is exactly the stuff that you've done a bunch of times on those vector problems, where we looked at the same vector in all these different orientations of the coordinate system. Okay? And then the y equation says negative 20 plus n is equal to 0. So n is equal to positive 20 newtons. And now if we want the force vector applied to the cart by the wall, notice that this vector here is the force on the cart by the wall. And so we just take that n we just calculated, plug it in here, and we get that the force on the cart by the wall is equal to 0.20. Any questions about that? All the subscripts, the crazy subscripts. Force on C by W. So on cart by wall. Any other questions? All right. So far, there hasn't been any distinction between an object sliding and an object rolling. But we know, like in our experience, there usually is a difference. And that difference comes from friction. And we haven't talked about that yet. So that's the next thing that we have to take into account. What if there's friction in the sliding motion between two objects? And friction you can break up into two different pieces. The first one is static friction. And that's the friction force that occurs to keep an object at rest. Okay, so if an object is at rest and you try to move it, there's a friction force that's applied to keep it from moving. And the other type of friction is called kinetic friction. That's the friction force applied to an object that's already sliding. No, it actually is trying to stop. Like friction is always trying to slow things down. But static friction is what happens when the thing is still, when you're trying to move it. And kinetic friction is the force that's applied when the object's already sliding. Anybody have a sense for which one of these can be? So static friction can be small, but if you max out, like, if you think about the maximum friction force that can be applied by static friction for any two objects, one of these two is bigger than the other one. Do you have a feel for what that is? Okay, so static friction is bigger, and that makes sense if you think about, like, when you're, like, moving to a new house or whatever, and you have big boxes of stuff, and you have a big box sitting on the floor. So imagine it's sitting there, and you go up and try to move it. It's harder to get it moving at first than it is to keep it moving. There's friction in both cases, but it's like you have to apply a big force to get it started. And then once it's started, you don't have to apply as big a force. And the reason for that is that friction is the development of, like, little molecular forces between the two objects. And if those two things come to rest, you can imagine those little molecular appendages managing to ooze into the spots and get a better grip on each other, Whereas if it's just sliding by, they never really get a good grip. So anyways, static friction is the bigger one. And kinetic friction is the smaller one. And just for the sake of time, we're not going to do any calculations with this. The calculations are pretty similar to the kinetic friction problems, but these are the ones that we're going to do. Okay, so the kinetic force of friction, that's what we're dealing with. Is a force vector that first is always opposite the direction of motion. So that means that it's in the opposite direction of the velocity vector. And that also means that the effect of kinetic friction is to, you can think of it as trying to stop the object. It's trying to slow the object down. So if you know the velocity of an object, or if you know the direction that the object's moving, you always know the direction of the velocity vector. You always know the direction of the friction force vector. So if an object's moving that way, friction is pushing it this way. That's just always how it is. It would be cool if sometimes the friction force would move in the direction you were moving. That would make everything a lot easier. But it's always trying to slow things down. So that's the direction, and then the magnitude of the friction force vector is this coefficient. For now, I'll just write it mu sub k. That's the Greek letter mu. It looks sort of like in between an M and a U. Times the normal force. Mu sub k is called the coefficient of kinetic friction. For every pair of objects, it's different. That's right. And yeah, you can just look it up for two objects, two materials that are in contact. So like you could look up the coefficient of kinetic friction for rubber and ice or something, and you can find a range of values on the internet. Steel and wood, whatever. Just two objects that are sliding against each other, you can find out that coefficient. Okay, so now this friction force is another thing that's going to appear when we do these calculations of an object that's sliding along a surface. And so now I'm going to give an updated list of the things that we know in these sliding problems. Okay, so first we know the normal force is equal to 0n. We already talked about that. Second, we know the acceleration vector is a0. We've already been using that. But the new thing is we know that the friction force is plus or minus the coefficient times the normal in the x direction, and then 0 in the y direction. And we know that because if an object is sliding and we have our y-axis pointing out of the surface, then the velocity vector needs to have only an x component. You know, if the surface is like this, the y-axis is like that, the x-axis is like that. Bless you. Then what directions can the velocity be? Well, the velocity, it's not going to jump off the surface or sink into the surface. So the velocity can't have any y component. And so the velocity can only be in the positive or negative x direction. And if the velocity is in the positive or negative x direction, the friction force also has to be in the positive or negative x direction, and just the opposite one of whatever the velocity is. So this has the opposite sign of the velocity. Okay, does it make sense? Yes.
I'm sorry, what was
Yeah.
number 1 on the list again?
So 1 and 2 are the things that we have already used. The normal force, the force that the surface applies to the object, always is just 0n. Okay, so for any two objects, the magnitude of the friction force is this coefficient that represents the objects times the normal force. So what that says is the harder two things are jammed together, the bigger the friction force is. Does that make sense? It does if you think like, so sliding this, well, that's pretty hard. I'm going to move it over here. So sliding this across the table isn't very hard if I don't put extra force on it. That's a horrible noise. This is better. Okay, that's not very hard, right? But if I push down on this, it gets a lot harder. And it's because the harder these two surfaces are pressed together, the tighter those molecular forces are, and the bigger the force is between those molecular forces that keeps this from sliding. Okay? Okay, so let me do a problem with friction. We'll see that it's essentially the same as that last example I did, except now we're going to have to deal with this new force that's the coefficient times the normal force. Okay, so let's say that we have an object sliding along a 20-degree incline. And let's say the direction of the velocity is this way, so that's the direction of motion. At this instant, it's sliding down the incline. And let's say there's a 1,000 Newton force pushing it into the incline. And let's say that for the material that this surface is made out of and the material the block is made out of, the coefficient of kinetic friction is 0.1. Oh, I didn't say the mass, but this is 10 kilograms. So the question is, what's the acceleration vector And then second is the object speeding up or slowing down. The coordinate system we're going to use has the y-axis pointing out of the surface like that. And so the x-axis has to be this direction. If it was the other direction, it would be violating the rules of coordinate systems that we talked about. And so let's draw a free body diagram of the block. Okay, so there's a weight force. So 98.1 down. And then there's the 1,000 Newton force being applied to the top. Then there's the pushing force from the ground. That's no different than it was before. I'll call that N. And then finally, there's a friction force that's parallel to the surface, that's opposite the direction of the velocity, that has a magnitude of the coefficient times this normal force here. So what direction is the friction force for this one? Yeah, it's opposite this direction of motion, so it's this way. The coefficient is 0.1, so this is 0.1 n. So Newton's second law, the 1,000 Newton force is in the negative y direction. So that's 0, negative 1,000. The normal force is, like it always is, in the positive y direction. The friction force is always in either the positive or negative x direction. Which one is it in this case? Positive x, yep. So 0.1 n, 0. And then we have to deal with the weight force. So the direction of the weight force is like that. This angle is 20 degrees. And so what's the angle that we want to use for the cosine and sine for this angle, for this vector? Negative 110 or positive 270 minus 20. So it's going to be 98.1 times cosine of 250. It's exactly the same as negative 110. And 98.1 times the sine of 250. And you get negative 33.55 and negative 92.18. That's all the forces. There's only 4 of them here. And so all these forces add up to be equal to the mass times the acceleration vector. Okay, so we have these two equations. Is there any way to know whether this is solvable? Yeah, you can do the y and calculate n, and then plug that into the top one and calculate a. That's the way we're always going to do it. The way you can tell whether you can solve it or not is we have two equations, so we can only have two variables. If we have more than two variables, there's nothing we can do about it. Okay, so the x equation says 0.1n minus 33.55 is equal to 10a. And the y equation says negative 1,000 plus n minus 92.18 is equal to 0. So notice, we always solve this by doing the y equation first. To find n. And then plug that into the x equation. So the y equation says n is equal to positive 1,092.18. Oh, that's a really big force. No wonder. In my one on here, it was 100 newtons. Anyways, we'll get a new answer. And now plug that into the x equation. So we have 0.1 times 1,092.18 minus 33.55 is equal to 10a. So 109.218 minus 33.55 is equal to 10a. Can someone solve for a for me? 7.57 meters per second squared. And at the beginning, I asked for an acceleration vector. And, okay, so now we're going to take that value for A and plug it into this acceleration vector. So the acceleration vector is 7.57 meters per second squared, 0. Okay, so now how do we know whether it's speeding up or slowing down? Yeah, exactly. So, so for part B, to figure out if it's speeding up or slowing down, the question is, are the velocity and acceleration in the same direction or the opposite directions? In this case, we have an acceleration that's in the positive x direction up the ramp. Okay. And the motion says the velocity is in the negative x direction. So the acceleration vector is like that. The velocity vector is like that. So it's slowing down. Any questions about that? Yeah. Yep. Is that far enough? Okay. Okay, let's do another one. So let's say this incline has an angle of 10 degrees. And there's a block on the incline that's connected by a cable to a hanging mass. Let's say this is 1 kilogram. The hanging mass is 2 kilograms. The coefficient of kinetic friction between the 1 kilogram block and the incline, let's say that's 0.2. And let's say that the direction of motion at the instant shown is up the ramp. So let's calculate the acceleration vector. And second, figure out if it's speeding up or slowing down. We've done a problem or two like this before where objects are connected over a pulley like this. And remember that one thing that we're going to have to take advantage of is that we know whatever the acceleration of this one is in that direction matches the acceleration of this one in that direction. Okay? Or if this acceleration is this way, it matches the acceleration of this one this way. Okay, well, let's start with the incline. So I'll do a free body diagram of the 1 kilogram block. Yes. Yeah, we're going to have to do both of them anyways. For this one, our coordinate system is going to have the y-axis pointing out and the x-axis like that. By the way, when we get to the hanging mass, there's no reason we have to use this same coordinate system, and we're just going to switch to a normal coordinate system for this one. Okay, so free body diagram of the 1 kilogram. There's a weight of 1 times 9.81. There's a pushing contact from the incline. There's a friction force. Since the velocity vector is up the ramp, the friction force has to be down the ramp. And that has a magnitude of 0.2 times n. And then if we include a little stump of the cable, the tension force is right out of the stump, and it has a magnitude of T. Anybody have any questions about the free body diagram?
So what again does the N stand for?
Normal. Yeah, normal means perpendicular, so it means a force that's perpendicular to the surface. So Newton's second law. What direction is that cable force in? In the negative x direction, yep. So that's negative T0. That n always appears the same, just 0n. The weight force, I'll get to that last. What direction is the friction force? Positive x. So 0.2 n, and then 0 for y. And now we have to think about that weight force. In this coordinate system, this angle is 10 degrees, the one in red. So what's the counterclockwise angle to get from the positive x-axis to the vector? (280) or negative 80? And so, let's see. The magnitude is 9.81. So the vector is 9.81 times the cosine of 280 and sine of 280. Can someone calculate this? I just made this problem up. Okay. Okay, so that's the weight force. So 1.70 negative 9.66. And now we're done with all the forces. And those have to be equal to the mass times the acceleration vector, which is always just A0. The y equation says n is equal to 9.66. And so now we can plug that into the x equation, and we get negative t plus 0.2 times 9.66 plus 1.70 is equal to a. So let's simplify that a little bit. can someone calculate 0.2 times 9.66 plus 1.70? .63. Okay, so I'm going to rearrange this as negative t plus a is equal to negative 3.63. And I'm going to call that equation star. Okay, so we can't get any further. We've already used our first equation. So here we are in our second equation. It's one equation with two variables in it. We can't get any farther on that. So now what are we going to do? Now we're going to isolate the hanging mass. And we're going to come up with a second equation, hopefully with these same variables that'll let us solve for this. So free body diagram of the 2 kilogram now. Okay, so here's the picture again. So now we're isolating the 2 kilogram box. There's a weight force of 2 times 9.81, so 19.62. And the only other place where there's contact with the boundary is the cable force. And since that's the same cable as the one attached to the other one, we'll represent it with the same T. The magnitude has to be the same. All that pulley does is change the direction. Any questions about that free body diagram? All right, so now we'll go to Newton's second law. And we're using the standard coordinate system for this one. So what direction is t? Positive y. The weight is in the negative y. And that's equal to the mass times the acceleration vector. Okay, well, if we get a positive value for this variable a, we've decided that 1 kilogram box will be moving in the positive x direction. Okay? And so if that 1 kilogram box is moving in the positive x direction, what direction will the 2 kilogram box be moving? If this is moving down the ramp, this is moving up.
It's moving up the ramp, so it's going down.
Well, it's moving.
You have motion going in the negative x direction, correct?
That motion represents the velocity, and the acceleration and the velocity are two different things. They can be
Oh,
independent
you're
of
talking
each
about
other.
acceleration. I've spaced out for a moment.
Okay, right. So this is the thing that matters here, is we're saying if we have a positive value of a, the acceleration vector is in the positive x direction. So a positive value of a means this box is moving down the ramp. And so a positive value of a has to mean that this box is moving up. Okay? And so if this box is moving up, that means an acceleration vector in this coordinate system of 0a. And so we're going to represent this acceleration as 0, positive a. Getting this right is important. we have two equations. The x equation says 0 equals 0, so that doesn't help. The y equation says t minus 19.62 is equal to 2a. And so you can rewrite this as t minus 2a is equal to positive 19.62. I'll call that equation double star. Yeah, that would make sense. You're just thinking a step ahead of me, that's all. I just set it up as two equations, and now we have a system of two equations for the same two variables. Now we can think about how to solve it. So now we'll just solve the system star and double star. Okay, well, the way I have it, you can get this pretty easily if you just add these two equations together, so I guess that's what I'm going to do. That'll make the t's go away. So substitution always works, though. But in this case, so add those two, the t's go away, you get negative a is equal to 18.99, I think 15.99. Yeah. No! Which one should? Yeah. Thank you. Yep. So then that means that this should be, okay. Let me just get it down before I forget, and then I'll. Yeah, so I subtracted a from both sides, so this should be negative. Then I subtracted the constants to get it over on the other side. And then I added, you can do this by substitution, but I added these two equations together. That canceled the t's. It left us with negative 3a is equal to positive 15.99. And that means that a is equal to negative 5.33 meters per second squared. Okay, so what's the acceleration vector of the block on the incline? We'll just plug that value of a into this. That's our acceleration vector. So the acceleration of the 1 kilogram block is negative 5.330 meters per second squared. Okay, the next question is, I just asked, I think, what the acceleration, oh, no, I didn't. So yeah, if you wanted to solve for the acceleration for the 2, you would take that a vector and plug it into, or I mean, you would take that a variable and plug it into your acceleration vector from the second Newton's second law, and you'd get something with the same magnitude but a different direction. Okay, so now the next question is this block speeding up or slowing down? Well, we have it moving in the negative x direction. The acceleration is in the negative x direction. The motion was in the negative x direction, so this is speeding up. The velocity vector was that way. The acceleration vector was that way. So it's speeding up. So even with the presence of that friction, that 2 kilogram mass pulling down on it is enough to make it speed up, moving up the incline. Any other questions about that one? Okay, let me give you one to work on for a few minutes. So let's say we have an incline of 30 degrees. What?
We're having issues. Don't worry.
Can I help in any way?
What was your question?
The part that's important to get right.
Yeah.
Will you explain that?
Yeah. Okay. So because these two things are connected by that cable, motion of one determines the motion of the other one. Okay. So if you take that 1 kilogram mass and move it an inch down the ramp that way, this goes an inch up, right? And so what you have to do is, when we represent the acceleration of the one in the incline, we're always going to treat that as A0, right? And then the A will work out for itself. But this is what we're always going to do. So then when you go to the hanging one, you have to think about it like this. If that variable A is positive, okay? So if this is 5, okay? What's the acceleration going to be of the hanging mass? So if this has an acceleration of 5 in the positive x direction, this has to have an acceleration of 5 in the positive y direction. And so if this is going to be written as A0, the acceleration of this one has to be 0A. Okay.
Thank you.
Okay. Any other questions about that one? Not right now. I mean, we can talk about it later and stuff. That's a hard problem. We're going to do a lab where we have to do that calculation. So, I mean, you'll get used to that calculation. But also, we did an example like that before we talked about friction, where you had to do that same thing with the acceleration. So, you might want to just look back at the example problem from a few classes ago where I did that. Okay, so let's say that this has a mass of 5 kilograms. And let's say there's a 10 Newton force pushing it up the ramp. and the motion is down the ramp. The coefficient of kinetic friction between the block and the incline is 0.1.
Does that have units on it?
No, it does not. If you look at, you can make sense out of that to yourself this way. If you look at, okay, you know that the magnitude of the friction force is the coefficient times the normal force. And the normal force has units of newtons, so you know that the coefficient can't have any units. So it's just a number. So what's the acceleration vector of the block? And second, is it speeding up or slowing down? Okay, so see if you can work through that together. Ask me questions if you get stuck, that kind of stuff. Yes? Yeah, okay, so that's sort of an important question because it has to do with where that velocity comes from. I think the best way to think about it is an object's velocity. So think of the acceleration and the force. Those things are happening at this instant, okay? But the velocity comes from what accelerations and forces have been happening up until that instant, okay? And so the motion could be this way because up until this exact instant, there's a big force applied this way that got it going, okay? So anyways, what's happening exactly at this instant that we have a snapshot of isn't a factor in deciding what that velocity was.
So you're saying like it could have essentially like been like thrown out there and then now it's like on its way back, but there's still time.
Yes. Yep. To sort of tell whether you're on the right track or not. Okay, so first, free body diagram. There's a weight force of 49.05. There's a normal force. The friction force is up the ramp. And then there's an externally applied force of 10 newtons. So Newton's second law, the 10 is in the positive x direction. The normal is 0n, like it always is. The friction force is in the positive x direction. The weight force so there's the x-axis, there's the y-axis. This angle is 30 degrees. So the angle is 240 or negative 120. And the weight force is 49.05 times the cosine of 240 and 49.05 times the sine of 240. Can someone tell me what that is? What is it?
Negative what? Help him out.
Negative 24.5. Okay. $42. Okay. So this is negative 24.5, negative 42.5. And that's all equal to the mass times the acceleration. So the y equation says the normal force is equal to positive 42.5. And then plug that into the x equation. And it says 10 plus 0.1 times 42.5 minus 24.5 is equal to 5a. And so 14.25, I think that's just negative 10.25 is equal to 5a. So that's 2.05. A is equal to negative 2.05. Is that right? Yes. And so then the acceleration vector is negative 2.05 x 0 y. Is that in the same direction or the opposite direction of the motion? They're both in the negative x direction. So velocity and acceleration are in the same direction. So that's speeding up down the incline. Any questions about that? Okay, so now you can work on all the problems in free body diagrams and Newton's second law.